welcome everybody and thanks for the introduction, Shanna. Yes, I'm presenting this talk about regionalization and the water issue because we developed a regionalized impact assessment for water consumption, and we faced a lot of problems of regionalization, and I will present you what we learned of and where still challenges remaining. So why regionalization is required? As Shanna said, I claim somehow for water it is absolutely required because on the global level we have no water scarcity. So on global average the water is not scarce at all. But if you look at the specific regions, we face sometimes very high water scarcity causing a lot of problems. That's one reason. But we also have 3 different impact pathways to follow because water use is not just a resource, it's also vital for human beings as well as ecosystems. So we have to follow different impact pathways which have also different levels of regionalization. So I would also claim at this point that archetypes is very difficult to define for water use, because if we have all the different impact pathways, these archetypes will also add to a large number. So regionalization is also required for the reason because it's a new topic and it's in agriculture. So that means agriculture has a lot of regional different inventories because water use is very varying along the globe. So we have some regions where we have no irrigation at all. We have other regions where there's a lot of irrigation. So also the inventory is very much affected by regional aspects. So if you look at the capabilities of regionalization, so regionalization or regionalized LCA will allow you to assess where the same process, like if you say corn production for instance, will have different impacts. So where will it have the lowest impact, where will it have the highest impacts? You could also define which supply chain, like if you have supply chains in different regions, you might have different processes, but also the processes will have different emission or irrigation requirements and impact factors. So that's a completely new topic, and we also have the uncertainties which has to be covered, and this is especially relevant in regionalized LCA because we have some new aspects of uncertainties, which I will explain later on. So regionalized LCA will explain that, so at the moment I think it can't. So that's some challenges why it can't be solved. So we have a lot of complexity. I think Thomas also introduced that we have much more data requirements if you want to do regionalized LCA. We have also, especially for the inventory, that's a lot of work, but it's also for the supply chains because they are somehow connected to social economics. So in certain regions we know there's different power production, but there's also different settings of the economy, the trade is different, and different processes are used. So it's a lot of new structural changes also in the life cycle assessment, life cycle inventories. And the uncertainties, it's really difficult to have it both assessed on inventory and impact assessment level because most impact assessment methods don't talk about uncertainties. So there's a new kind of uncertainties. It is picking the wrong location. If you have an impact factor and you have inventory data, and you might not get the right impact factor for the location because the definition of the location might result in a mismatch. And probably the most important limitation so far is the software implementation, which is lacking. So that's under development, but still not available so far. So about the topic with the spatial resolution. So if we want to have regionalized impact assessment, we usually use raster data sets. So that's like a map with pixels, or you can say it's a table having the different pixels of the Earth. And if we have a feature, usually it's a shapefile. So we have like here we have a watershed, for instance, and then we want to have this shapefile converted to a raster data set, resulting in this kind of picture that we have a yellow and a green watershed, and then we have to connect it to the inventory. So we do our calculation of impact assessment on the raster level, and then we have an inventory which might be a country. So the country might have overlap with different shapes or different impact factors, so which shall we apply? So there's the option that we just take the green one because there's a larger overlap, or the yellow one, or we probably just need to have a weighted impact factor for that kind of data, inventory data. Or we might have very explicit inventory data specifying points by coordinates, and we might pick the wrong locations because the raster resolution changes the shape of the watershed. For instance, if you're in a country, you probably know which country you're in, but if you have a watershed, you might not know which watershed it is because it's not so obviously visible. So the resolution to that problem is that we have to maximize, the solution is that we have to maximize the resolution of the calculations, and we need to have the weighted impact factors for the country. If you have a shapefile or country data, we need not base our results on average data and do the calculation on national average data for countries, but we need to do it on very high spatial resolution and then finally aggregate it based on a weighting on country level. So that's one point, to have the highest possible resolution, but it's not the only important point because we also have to select the proper data. We have, for this use availability ratio of water, that's somehow behind all these water assessment impact assessment methods. We can pick data on country level from national statistics, and we will have a ratio which results in a map like that, or we can have it on watershed level. That's the middle map that we have. That's all the same calculation behind and results in different data. So that's the red areas are very high water scarcity, green almost no. And we see that there's a huge difference if you take the national average. Like for the states, we have some regions where you have high water scarcity, others not. And usually the non-water stressed areas are also not so important regarding water use, because in most areas which have low water stress, there's also low water use, and vice versa. I mean, the high water use is finally resulting to the high water scarcity. But then we can say, okay, we take the highest resolution possible, which is also on a raster level available, but then we might miss the crucial point of the calculation, because this is not just taking one point on the map, because we have a downstream-upstream problem if we talk about water use. So we have watersheds. Water might come from mountainous areas where there's no water use. It flows to the cities. There's a lot of water use, but that can still be on specific location. It can be overuse of water, but if you look at the whole watershed, it's not a problem, because also nature is using, at some places, all the water available in the watershed, and in other places not. And on the other side, you can say, even if we don't have a water problem in the mountainous areas, but it leads to very scarce areas downstream, also the people living in the water abundant area have some responsibility to limit their water consumptions. So the second maxim, I would say, is not to select only the highest resolution possible, but also to select the proper resolution. So I just want to shortly talk about the impact assessment, but this is not the main point of this talk. So we developed the impact assessment for midpoint and endpoint indicators. We have separate calculation factors for more than 11,000 watersheds. So that's on global coverage, and the data is published, so you can have a look at it. We have also, for better ease of use, we have Google Earth Layer. You can download, you can